Okay, welcome again. We are going to discuss about the formulation of an LPP now. Okay, so how to formulate an LPP problem. That's what our aim here. So look at this. This is a real life situation we are seeing there. Okay, so here this is a factory situation where there are four types of products are produced in that particular factory, and for that to make the four products, um, each product has to go under three machines called A, B, C, three machines, and it has to use the current. Okay, it has to use the current uh, to make these machines. When this product comes to this machine, it takes 3 volts. When this product comes under this machine, it comes to 2 volts, like that. So this figure gives us the current that takes different machines for different products. That also given to us. Next one is about P1, P2, P3, and also look at that. The product from the first product, the profit from the first product is given here is rupees 3. The profit from the second product is rupees 4. Product from the third product, or profit from the third product is 6 rupees, and the profit from the fourth product is given as 2 rupees. Okay, so the profit for the products also given here, the data. Then what are given there? The maximum current needed for machines A, B, C are given like this. So maximum, okay, so maximum current needed for each machines A, B, C are given as 800 volts, 200 volts, and 700 volts. Look at this picture here. Here the maximum availability of the machine A is 800 volts, and 200 volts for machine B, and 700 volts for machine C. Okay, such a way the data are given. What is our question now? What is our aim here? That's what we are interested. Okay, what is our aim here? Now our aim here is that find the number of products P1, P2, P3, and P4 have to be produced so that the maximum profit we get, the maximum profit we have to get. If that is the case, how much number of products first, how much number of products second, and how much number of products third, how much number of products fourth have to be produced so that the maximum profit we get. Okay, the maximum profit we have to get. That is our aim here, and we have to make an LPP model for the situations. We have to make an LPP model for the situation. Okay, so how to make this LPP model? Okay, that's what we are interested. Now look at this. Look at this. How can we make this the full view we need there? Let we have a full view, then only we can make the questions pattern seeable to you. Otherwise, it will not be looking to you. Now, what I am assuming at first, okay, what I am assuming first is that I am assuming that x1, x2, x3, x4 are the number of products 1, products 2, product 3, and product 4 which gives you maximum profit to the company. X1, X2, X3, X4 are the number of products respectively P1, P2, P3, P4, which gives a maximum profit to the company. That way we are assuming. Okay, so if that is the case, what is given here, the profit for 1 unit of product 1 gives 3 rupees, and 1 unit of product 2 gives 4 rupees, and 1 unit of product 3 gives 6 rupees, and 1 unit of product 4 gives 2 rupees. So how much number of products we are making, we don't know. We are just assuming, that's all. Suppose that is assumed as x1, x2, x3, x4. Then what I will get is that if x1 is the number of products that gives maximum profit to the company, then 3 into x1 will give you the profit from the first products. Similarly, 3 into x2, so here 4 into x2 will give you the total profit by P2 to the company. Similarly, 6 into x3 will give you the total profit given to the company by the product 3. And last one, 2 into x4 will give you the profit by P4 to the company. So if you add all of them, I mean 3 into x1 plus 4 into x2 plus 6 into x3 plus 2 into x4 will give you the total profit to the company. Am I correct? The total profit or total income to the company. And what is our aim? Our aim is to maximize it. Our aim is what? To maximize it. Am I correct? So the objective function is that maximum is at equals 3 into x1 plus 4 into x2 plus 6 into x3 plus 2 into x4. That is what we say the objective function. Now look at that. We will have the objective function first. So objective function is maximum is at equals 3x1 plus 5x2 plus 6x3 plus 2x4, where all of them x1, x2, x3, x4 must be greater than or equal to 0, because x1, x2, x3, x4 are the number of products produced by the product 1, product 2, product 3, product 4. So never goes negative. Only the product can be made or cannot be made. So the value of all these variables must be greater than or equal to 0. Now what about these constraints now? Look at this table. Look at this table. The constraints are the current capacity of the machines. Am I correct? Consumption of current by the machines. The conditions given here. Machine can take only 800 volts, and machine B can take 200 volts, and machine C can take 700 volts only. Am I correct? Look at this. Machine A can work for 800 volts. Machine B can work for 200 volts, and machine C can work for 700 volts. So how much quantity of the first product goes to first machine? We don't know. So if 3 into x1 will give you the total consumption of the current for the product 1. 4 into x2 will give you the total consumption of the current for product 2. 8 into x3 will give you the total consumption of the current for the product 3, and product 4 takes 6x4 as the total current from the machine A or for the machine A. Okay, so if you add all of them, the maximum current availability is given. Am I correct? So the total must not go above than that. The total must not go above than that. I mean 3 into x1 plus 4 into x2 plus 8 into x3 plus 6 into x4. If you add all of them, that will give you the total current consumption by machine A. That should not go more than 800 volts. Okay, so that is what one of the constraints here, that we are doing like this: 3 into x1 plus 4 into x2 plus 3 into x3 plus 6 into x4 must be less than or equal to 800. That's what we see here. 3 into x1 plus 4 into x2 plus 8 into x3 plus 6 into x4 must be less than or equal to 800. Okay, 3 4 3 6 3 4, sorry, this is not 8. We can take that as a 6, not a 8. Okay, so this is what 3. So 3x1 plus 4x2 plus 3x3 plus 4x4 must be less than or equal to 800. Okay, that's what we have to understand. Okay, so that's what we have, the first constraints. So constraints: 3x1 plus 4x2 plus 3x3 plus 6x4 is less than or equal to 800. In the same way, come to the second machine. The second machine, if you multiply this 2 volts by how many number of products we are making from the first two products, then multiply 2 into x1 will give you the total consumption of the current for the products 1 by the machine B. If you multiply 2 by x2, that will give you the total current consumption for the second products under machine B. 7 into x3 will give you the total current consumption for the product 3 under machine B, and 5 into x4 will give you the total consumption of current for the product 4 by the machine B. So if you add all of them, I mean 2x1 plus 2x2 plus 7x3 plus 5x4, and that total must to be less than or equal to what is given here is 200. Am I correct? I mean 2x1 plus 2x2 plus 7x3 plus 5x4 must be less than or equal to 200, and that is what the second constraints. Okay, 2275, that's what we have there. 2275, 2x1 plus 2x2 plus 7x3 plus 5x4 must be less than or equal to 200 volts given there. So that is what the second constraints. Coming to the third constraints is based on the machine C. So total current given to the machine C to operate is 700 volts only. 700 volts only. It cannot go more than that. That is the distribution given to the machine C. So 6 into x1 will give you the total consumption of the current for the product 1 by the machine C. 4 into x2 will give you the total consumption of current for the second product under the machine C. 7 into x3 will give you the total consumption of current for P3 under C, and last one, 4 into x4, will give you the total current consumption for P4 under the machine C. Okay, and that must be less than or equal to 700 volts. Okay, so that's what we have here. Look at that. 6x1 plus 4x2 plus 7x3 plus 4x4 is less than or equal to 700. Okay, so these are, we call it as a constraints, because these are the very barriers on our situations, and this is our objective function. Our objective function is to maximize this function z equals 3x1 plus 5x2 plus 6x3 plus 2x4, and the totality of all we call it as linear programming problem. Okay, the totality of all what we call is the linear programming problem. So linear programming problem consists of objective function. The first one is about the objective function. Linear programming problem consists of the objective function, here the fusible condition, and these are the constraints. Okay, so these are very, very important that we have to understand. So with that we can get to the formulation of LPP problem. Okay, so this is how we can get the LPP problem can be derived like that. Okay, so just a quick recall what we have studied now. These are the data given to us, and for machine A, machine B, machine C, we have a constraints. This can work only 800, here 200, 700. So P1, P2, P3, P4 are the four products, undergoes the action of three machines. So if you multiply them, this and this, this and this, this and this, this and this must be less than or equal to 800, because 800 volts only available. And this, that multiply this and this, this and this, this and this, this and this, add and less than or equal to 200, and last one is multiply add less than or equal to 700. To get to the objective function, the profit terms are given here. 1 unit of product 1 gives 3 rupees, and 1 unit of P2 gives 4 rupees, and this 6 rupees and 2 rupees. If you multiply how many, x1, x2, x3, x4, we don't know, we have to solve them, then only we can get. So if you multiply this by 3 rupees, this by 4 rupees, this by 6 rupees, this by 2 rupees, you'll get 3x1 plus 4x2 plus 6x3 plus 2x4, and that function I am adding as z. My aim is to maximize it. Okay, so finally what I am getting is that this I will get. Okay, this is a set of equations, constraints I will have, then objective function I will have, then this is called fusible condition. The set of these we call it as a linear programming problem, because all variables power is only one, therefore we call it as linear programming problem. Okay, so with that I have to come to the end of this session. Thank you.